Okay, so now we're going to take our enolate ion and I'm going to add either the ketone or an ester. All right, and so what I want here is the full reaction mechanism for these two reactions. So take a minute and do that on your own, and then we'll go over it together. Of course, mechanisms, as you know, we were talking about, look at the study guide. Most of those reactions have stars next to them. We have to know the mechanism for. The good news is that there's this like common pattern that we see a lot. So let's sort of just go over those. But yeah, I'm going to give you a few minutes to do this on your own, and then I'll show.
I'm finally back.
Cool. All right, so we're doing mechanisms for when you take an enolate ion and combine with a ketone or with an ester. Very like closely related but not identical reactions take place.
So like the negative charge, wouldn't it attack the carbonyl carbon on the ketone?
Yeah, so actually on both of them, it will attack the carbonyl carbon. Oops, I'm going to use different colors here, so hopefully. So on both of these, what's going to happen is the carbonyl carbon is going to get attacked. And what does that form? What's that intermediate called? Oh, whoops, so let me just complete this. Carbon can't have more than 4 bonds, so that's going to kick that up there. Same thing over here. So this forms what intermediate? Did I not drive you guys crazy saying it over and over again during the lecture slides?
Nah, not really.
Is it the enolate or something like that?
So it's the tetrahedral intermediate.
Oh, got it.
That's what I'm going for here. Every time a carbonyl carbon gets attacked, you form a tetrahedral intermediate. And the reason why I want to sort of hammer this home is because when you see a tetrahedral intermediate, you're always going to ask yourself what question?
Is there a good leaving group?
Boom, absolutely, yeah. So that's why I sort of am trying to drill this into your head, is because whenever you have this carbonyl carbon getting attacked, it's always going to form a tetrahedral intermediate. And then your next step that's going to sort of inform what you do is ask yourself that question: do I have a good leaving group? So over here in the red, when I took my ketone, do I have a good leaving group?
No.
No, right? So these are all carbons. Carbon is not going to be a leaving group, right? You got to be a heteroatom to be a good leaving group. So the only thing that can happen from here is to protonate this oxygen, right? So if you don't have a good leaving group, your only course of action is to plug up this negative charge with a hydrogen. So in this case, that's exactly what happens. What about over here in blue when I had my enolate ion reacting with an ester? Again, I'm going to ask myself, do I have a good leaving group?
I would say yes.
Yeah, in this case, we have this heteroatom, the oxygen, that can act as a leaving group. And so this is going to come down and kick that off. Okay, so this would have been an example of an aldol addition. This would have been a Claisen condensation. And what's one of the things that we talked about as to how I can double check that I've actually positioned that I've got the correct product? Sort of two ways to double check, right? First, count carbons. Just definitely always go through and count carbons because that's the easiest way to make a mistake. 1, 2, 3, 4, 5. So that would be these 5. I'm even going to color code where things came from to make it clear. And then over here, I have 1, 2, 3 carbons. 1, 2, 3. Okay. For the Clayson, I'm going to get rid of this chunk of my molecule. So the only carbons that should be accounted for in my product are these 2. And so indeed. Okay. And then there was another way that we talked about, because of course these products that we're forming are these big ugly molecules. What's another way that we can double check that we've gotten our correct product, and in particular that our functional groups that we've created are correctly spaced?
Is it that like 1, 3 counting?
Yeah, so they should be 3 carbons apart. So always start numbering from the carbonyl carbon towards the other one. 1, 2, 3. Same thing over here. 1, 2, 3. And the new bonds that you formed are between carbons 2 and 3. And so that checks out. Here's my new bond, and here's my new bond. But yeah, so those sort of 2 things will sort of prevent you from making stupid mistakes. 1, count carbons. That's a good strategy anytime you're doing reactions. For these particular reactions, the aldol and Claysons, you would you're looking for those functional groups to be 3 carbons apart. And then with my aldol, there's another reaction that can happen, which is if I just have same basic conditions, but then I hit it with heat. And what's that going to do?
It's going to get rid of the alcohol group and make a double bond.
Yeah, absolutely. And again, that double bond is going to be positioned between carbons 2 and 3. So that's just another kind of way to check. But so yeah, so oops, I'm going to give myself more space. Andres, you can't see the bottom of the screen.
No, we can't see that.
Up. Can you see down here even?
Yeah, I can see it now.
Okay. So there, that would be my right. So this is the addition, and this is the condensation for the aldol. Now the Clayson reaction is called a condensation. It kind of drives me nuts, just because for the aldols, the condensation step is the formation of that double bond. For the Clayson, it's more analogous to an aldol addition than it is an aldol condensation, but I didn't invent the language, so that's just how it goes. Okay, cool. So that's, I mean, yeah, doing that and then also going backwards. Let's actually just do an example of that. So. Okay. If this is my aldol addition product, take me back to what my reactants were. Actually, and go ahead, just to be a pain in the butt, go ahead and name it too. So that's also something we should be able to do.
So when we say the reactants that form that, so is it going to be cut into two parts down?
So you're definitely gonna break a bond, right? So let's figure out which bond we're gonna need to break.
Is it the second carbon bond that's between both of them?
So again, like this is maybe I don't quite know what you mean, but a great strategy for this is similar to before. Go through and number your carbons, starting at the carbonyl carbon 1, 2, 3, and then where is my new bond always formed between?
2 and 3.
2 and 3, yeah. So this bond here needs to be broken. So let me even kind of just start out with this, and then I'll erase. Oops. Okay, so I'm going to get rid of this bond here. And what else do I have to do? This is close, but not quite there.
Okay,
So that alcohol, it's going to be that like double bonded oxygen.
Yeah.
So then does that close the ring there? If
it
goes
doesn't
down,
close the ring. So basically this, right, this was my new bond was here. That means that this carbon right here was the nucleophile, and this carbon here was the electrophile.
Oh.
And the electrophile was a carbonyl carbon. So that OH group, that alcohol group, should be a ketone instead, or an aldehyde in this case. But notice that this was an example of an intramolecular one, because I still have these carbons here that are connecting everything. So obviously the way that it's written here is a little weird. 1, 2, 3, 4, 5, 6, 7, 8. It should have an 8 carbon chain. That's an aldehyde on this end. And then 1, 2, 3, 4, 5, 6. Have another carbonyl group over there. And then how do I go about naming these compounds when I have these two functional groups, both a ketone and an aldehyde? Which one's going to win?
The aldehyde?
The aldehyde is the higher priority group. And then the ketones, instead of being referred to as the own suffix, we're going to use the oxo prefix. So this is 6-oxo-octanal. Okay, but this, and if instead of being an aldehyde, like the product of an aldol addition, let's just do the analogous one. But we have this, actually this wouldn't be like that. Again, you can use that same sort of strategy of numbering the carbons, starting out with the carbonyl carbon. This one, you want to start out with the one that's still attached to the ester. 1, 2, 3. Again, this is the bond that formed. So I'm going to break that apart. But then this would be, if this was an aldol addition, this example here would be of a Claisen condensation, right? And just sort of reviewing what we did at the beginning here. The difference is that with a Claisen, you're starting out with an ester, and with an aldol, you're starting out with a ketone or aldehyde. So in terms of the retrosynthesis, I'm just going to make sure that I have, I'm going to make sure that I have an ester that's formed. And so in this case, again, let me just be sure, 1, 2, 3, 4. This is accounting for this half here. And then this side is also going to be an ester. And this chunk here is the chunk that left as a leaving group when the reaction took place. Okay. Let's do an example of alkylations. All right, and so the difference here in both of these situations, we're going to be adding on an alkane. But what happens if we do it at cold versus hot, right? So this is the kinetic versus thermodynamic kind of considerations that we have. When it's cold or at low temperatures, which alpha carbon gets alkylated? Green or blue?
Cold, the green one?
Yeah. So cold, right? Low temperatures. This is kinetic, the kinetic controlled one, which means that it's whichever one is going to happen faster. Okay. So the reason why the green would be at, this is again just to color code things. The green position is considered the faster position is just because it's less sterically hindered. So at low temperatures, alkylation will occur at the less sterically hindered carbon. So in this case, I'm going to need 1, 2, 3, 4. Under warm conditions, this is what we call the thermodynamic, which is going to be whichever one forms is more stable. And so in that case, it's going to be the more highly substituted position.
So like, what if they were both the same? So like, what if it was just a ketone, but without the other carbon?
So if it's a symmetric molecule, something like that, that's what you mean?
Yeah.
Yeah, then you're going to get the same no matter what.
Okay.
Another example would be like if it's an aldehyde, well, then you only have one alpha carbon. So that's also going to give you one product.
Mm-hmm.
Okay, what about this molecule here? What would we expect to happen if I tried to alkylate that at hot and cold temperatures?
I say in cold, there's gonna be no reaction because it's a tertiary.
So
Would they just be the same?
What's up?
Would they just be the same because it has no other option?
Exactly. Yeah. So it's not that there's going to be no reaction. It's that it's always just going to be the same alpha carbon because it doesn't matter. There's no kinetic thermodynamic consideration. There's only one alpha hydrogen or only one alpha carbon that has any hydrogens on it. So in this case, the two products, just like in this example and this example, you would expect to get the same product no matter what conditions you used.
Oh, all right. Because I think on the discussion, I think I put no reaction on that. That's the only thing.
Well, good. I'm glad we went over it.
Okay.
Okay, so if there's only one alpha carbon that has hydrogens, that's what you're going to choose. Otherwise, as if it, like in the example up top, you have that kinetic versus thermodynamic considerations. Now, I kind of did it a little sloppily in that I didn't include all of my reagents. We actually use a different base when it's cold. We use LDA, negative 78 degrees Celsius, and then we'll follow it up with our alkene. If under warmer conditions, we use sodium hydride, still not like, oh, whoops, 25. Still not terribly hot, but I was kind of more trying to emphasize the difference between this kinetic versus thermodynamic idea. So, you know, we do use different bases. That's a good sort of thing to look out for, but you should also understand, you know, what's doing the controlling. Again, it has everything to do with the fact that this side, the green side's more accessible, so it will react faster, but the blue side creates a more highly substituted molecule, so it's more stable. Using these alpha beta unsaturated. And note that like one of the things to keep in mind, right, about why, you know, just to kind of in all the complicated ways that this can show up, we actually know how to make this compound here, starting with an aldehyde or ketone. So actually the first thing I want you to do before we do any reactions of alpha beta unsaturated is to do the retrosynthesis on this and show me what my reactants would be to create that. Actually, I think it was this, but this is basically just the example we've already done, right? So hopefully wasn't too bad, but if I'm going to go back one step, that would be my, so this would be after the aldol condensation. This would be after the aldol addition. And again, this would be an intramolecular reaction. Starting with our 6-oxo-octanol. Right, so just something to keep in mind if you know you're thinking about like these reaction wheels that I can put on the exam. We know not only do we know reactions of these alpha beta unsaturated aldehydes and ketones, we also know how to create them. Okay, so then for this, let's do two different things with it. First, hit it with an enone. Next, with a stabilized, not enone, sorry, enolate.
So I'm guessing it's always gonna hit the second carbon so that the carbonyl carbons can be 3 carbons away.
So the different, okay, so when we look at an alpha beta unsaturated, you should be thinking your brain should sort of notice, first of all, we have our normal old electrophilic site, the carbonyl carbon, right? We're very used to seeing a carbonyl carbon playing the role of an electrophile. The whole shtick about alpha beta unsaturated is that it has 2 electrophilic sites, the other one being this carbon here.
Okay.
And we can show that that's electrophilic if we use resonance structures, because this pair of electrons can jump up here. Oops, that should be an oxygen. And this pair of electrons, whoops, over here. And so that other resonance contributor would look like this. Right, so you see that because through this resonance, drawing these resonance structures, we're illustrating that this carbon here has this partial positive character. Okay, so again, the whole shtick of an alpha beta unsaturated is that it has two electrophilic sites. And yeah, one's the beta carbon, and then we have the carbonyl carbon itself. Strong nucleophiles, so for example, this enolate, will attack at the 1,2 position, that carbonyl carbon. Weaker nucleophiles, so for example, this stabilized enolate ion, they will attack at the beta carbon, what we call a 1,4 addition. Okay, so take a second and see if you can't give me those products. All right, so again, the stronger nucleophiles will attack that carbonyl carbon, and this is just the same sort of reaction mechanism that we would expect if it was a regular old aldehyde or ketone, not alpha beta unsaturated. You would first get your tetrahedral intermediate. You're then going to ask yourself what we always ask ourselves when we get tetrahedral intermediates. This was kind of ugly. Which is there a good leaving group? In this case, there is not a good leaving group. So the only thing that can happen is to protonate that oxygen. Oh, whoops. So notice that here, this double bond, in the case of the 1,2 addition, the double bond doesn't do anything for us. It's the exact same reaction as if it wasn't there. That's ugly, hold on. With the weaker nucleophiles, and in particular, the ones that you really want to be able to spot are these 1,3 dioxos, basically where you have your enolate ion where the negative charge is perfectly positioned between two carbonyl carbons. These will react at the 1,4 position or at the beta carbon. So let's go ahead and do that. different colors just to... All right, am I done? What's wrong with this step as I've written it here? That's one of the easiest ways that we can make sure that we've drawn our reaction mechanisms correctly.
You need to show where those other electrons are pushing towards.
Exactly right. So what the problem as written is that if I were to just stop there, I'm giving carbon too many bonds.
Mm-hmm.
Right? So you know that there's got to be at least something else that happens. And so what's going to happen is this pair of electrons will jump over there. And then I have the same problem. Carbon's got too many bonds. So this pair of electrons has to jump up there. Right? So it's going to be this sort of chain of reactions that pushes those electrons onto that oxygen. And again, as we were saying, this is the chapter of big, ugly products. So half the battle is just making sure you've gotten all your carbons correctly accounted for. Do something creative. And then notice that even, whoa, oh, whoops, there should be a double bond here. We effectively have gotten to our tetrahedral intermediate again. It's actually not a tetrahedral intermediate, but we have that negative charge on the oxygen. So just like before, we can kind of ask ourselves, is there a good leaving group? In this case, there isn't. So the only thing that we can do is to protonate that oxygen. Okay, but what do we call this right here, where we have a double bond located right next to an alcohol group?
Is it Enol?
Yeah, so this is an enol, and what do enols do?
Don't they rearrange?
Tautomerization.
They tautomerize, absolutely. And into what?
Is it a ketone or a carbon?
Into
Carbon?
ketone, yeah. So enol, keto, tautomerization. Basically, this hydrogen is going to move from the oxygen over to this carbon. So a tautomerization is just an intramolecular rearrangement. I'm not adding any new elements. I'm just rearranging the ones that are already there. So in this case, it will tautomerize. And this is in an equilibrium, but it generally favors the ketone. Tautomerize. Okay, and just to sort of compare the products that you get at the end of the 1,2 versus the 1,4, this is going to drive me crazy how ugly this is. I got to fix it. Okay, notice how on the 1,2 addition, we're left with our alcohol and ketone functional groups with that perfect 1, 2. That's not right. How did I mess that up? Oh, I just drew. See, that's why we count carbons. With the perfect 1, 2, 3 spacing, right? Just like we would expect for aldol addition reactions. Same thing for the 1, 2 addition. For the 1, 4, we actually have a ketone that's formed, right? So we don't have, our carbonyl carbon doesn't turn into an alcohol group, it stays a ketone group, and we've gotten rid of our double bond. Whereas in the 1,2 addition, we've actually kept our double bond and we've got an alcohol group. And actually, I mean, if there was any amount of heat involved, because of this product here, can actually get a condensation also. And actually the condensation would be particularly favorable for this particular molecule. Can anybody tell me why?
Because you can have resonance between all those bonds right there.
Yeah, exactly, right? So one of the reasons that condensation is favorable, period, is because the new double bond is in resonance with that carbonyl bond. But now I also have this existing double bond here, all of which could be in resonance. So this would be a particularly favorable condensation. Right? Anytime you have large resonance networks, molecules like that. And just to sort of this is, of course, what type of reagent that we've sort of covered for a while now?
Grignards.
A Grignard. So a Grignard would be an example of a strong nucleophile. Strong nucleophiles attack where on my alpha beta unsaturated?
At the carbonyl.
Carbonyl carbon, right? So this would be this carbon here. Whoops. I'm not going to do out the whole mechanism, but bottom line is you would get your tetrahedral intermediate. You would ask yourself, do I have a good leaving group? And you don't, so you're stuck. Okay. Now, another one that we just learned about is R2CuLi. This is called a Gilman reagent. And I kind of want you guys to think about it as being a weaker Grignard. So this would be a weaker nucleophile. And that's going, where do our weaker nucleophiles attack? The beta carbon. What's up?
Oh yeah, sorry, I didn't hear the question. Go ahead.
Oh, you're good. Yeah. So our weaker nucleophiles attack the beta carbon. And
Okay.
so in this case, my product would be that. I guess R, because I didn't specify. Okay. So here's this group here. There's this group here, right? So just to sort of go over this Gilman's reagent is sort of a newer one that we've had here. It actually was introduced not in chapter 21, but in chapter 20, because it reacts introduced in slide 59 of chapter 20, because it reacts with carboxylic acid derivatives. But instead of, let's actually just do them both. If I had a Grignard, What's going to be the difference between these two and how they react with our carboxylic acid derivatives? Anybody?
I'm not sure.
Okay. So first, let's do the Grignard real quick. We'll do the whole mechanism here. MgR. This is going to attack this. That's going to kick that pair of electrons up. That gives me my, again, just to drill it in everybody's head, my tetrahedral intermediate. And what do we do when we get our tetrahedral intermediate? We ask ourselves,
Do we have a good leaving group?
do we have a good leaving group? In this case, we do. It's that chloride, so that's going to kick that off. And so I'm left with this, an aldehyde or ketone. But importantly, aldehydes and ketones also react with Grignards. So I'll have yet another round of attack. And so the bottom line is that you'll have two additions onto your carboxylic acid derivative. A Gilman, again, is like a weaker Grignard. It can react once, but it's not going to react a second time. So you'll only get one group on there. So instead of getting an alcohol at the end of the day, like I would with my Grignard, you're going to be left with an aldehyde or ketone. Other random stuff to keep in mind, just kind of off the top of my head here. SOCl2 has shown its head twice in this lecture. Actually, and once before that. Okay. What do I get as my product in the top reaction? Oh, crap. I messed that up. Okay, so I would kind of group these guys together in your mind, because what SOCl2 does is it's a substitution for that hydroxyl group. It swaps out a hydroxyl group for a chlorine. So in the case of an alcohol, it'll make it an alkyl halide. And in the case of a carboxylic acid, it will make it a acyl chloride, right? But notice that in both of these, I've just swapped out my hydroxyl groups for a chlorine. What it does with a primary amide is completely different. It actually creates a nitrile group. So I guess I actually have to do it like this. Or these are the same thing, but yeah. So it, so I guess it doesn't. I wanted to say it oxidizes, but it doesn't do that. But anyway, it converts an amide into a nitrile. So it kind of does something completely different in there. So again, I kind of hold these two in the same place in my brain, and then kind of think of this one as a random little exception. Okay. And I guess just while we're on these nitriles, because they kind of, okay, so see, let's take what happens when I do the lithium aluminum hydride and what happens when I hit it with acid. Right, so this is sort of two common reactions that we can do with nitrile groups is either, again, what do we think of when we hear lithium aluminum hydride? That's reducing. So we can reduce this to an amine. 1, 2, 3, 4, 5. Running out of room. Whereas if it was with acid, it becomes a carboxylic acid. Cool. So do you guys have any other particular things that you want to see? It's kind of a random smattering of different practice problems.
I don't think so. I think I asked earlier in the office hours thing. Let me check.
All right, and in particular for chapter 21, what you really want to make sure you have down is those mechanisms for the aldol addition / condensation, as well as the Claisen. If you can do those correctly, it kind of, I don't want to say that you've completely got all your bases covered, but it means that you have a good understanding of the type of mechanisms that are seen in this chapter.
Okay.
Right, and in particular, go through that process of, I got my tetrahedral intermediate. Do I have a good leaving group? That sort of thought process is important, not only for this chapter, but also the previous chapter with the carboxylic acid derivatives.
Okay.